Hello, my name is Renzo Mondaini, and I live in Ravenna. I'm an electronics technician, and I work for a telecommunications company. In the evenings, I like to play at being an amateur scientist. Over the last year, I've been doing experiments on electrolytic cold fusion, which is a non-radioactive, low-energy nuclear reaction, and simple to carry out. You need a Pyrex glass container. Fill the glass with water and dissolve a substance to make the water conductive. Immerse two electrodes attached to a DC voltage supply of more than 150 volts, preferably adjustable. These two electrodes must be asymmetric. The anode should be immersed deeply and the cathode much less so, with a ratio of about 1:5 or 1:6. In order to make the water conductive, you can use any substance which dissolves and generates ions, for example, any kind of salt, acid, or base. Some substances do not lead to electrolytic cold fusion, as they do not generate ions in solution. These could be organic substances, for example, so sugar or vinegar do not work, as they are organic substances and therefore do not generate ions when dissolved. Ions are necessary to conduct electrical energy. I also discovered that bismuth carbonate does not work, as unfortunately it does not dissolve in water and therefore can't generate ions or function as an electrical conductor in an electrical cell. So now I'll show you electrolytic cold fusion as you've never seen it before. Electrolytic cold fusion can be carried out in a Pyrex beaker containing water with a salt solution. We can use sodium bicarbonate from the kitchen, or potassium carbonate, about 100 grams per liter. Electrolytic cold fusion starts with a simple electrolysis of the water. You can see the anode on the left, an electrode which has a positive voltage, cathode on the right, which has a negative voltage. Now I'll show you in more detail. I'll show you the negative electrode in more detail. I'll hold it with a dielectric glove and apply a voltage of 150 volts. You can see the electrolysis of the water, hydrogen at the cathode and oxygen at the anode. However, something strange happens if I raise the cathode. As you can see, if I raise the cathode, there's a concentration of positive ions, H plus hydrogen. H plus ions are simply protons that trigger these sparks, is subjected to certain current density. If I lower the electrode again, we no longer have this reaction, but simply electrolysis of the water. If I raise the voltage to 200 volts, you can see this illumination until the electrode becomes incandescent. $300 volts, 350 volts. This is a tungsten electrode. Now I'll show you how a zinc sulfate solution reacts. Anode on the left and cathode on the right. Increase the voltage to 100 volts. 150 volts, and you can see that the zinc is deposited on the cathode. We get zinc electrolysis. Zinc at the cathode, oxygen sulfate at the anode. If I increase the voltage to 200, 300, 350 volts, you get a formation of plasma. If I lower the voltage to 300 volts, 200 volts, 150 volts, you get electrolysis of the zinc sulfate with zinc at the cathode. If I increase the voltage again to 200 volts, 250, 150, we get plasma. Lower again, 300, 250, 200, 150, 100, we get zinc deposits. Now I'll show you a solution of copper sulfate. Insert the two electrodes, anode on the left and cathode on the right. Apply a continuous voltage of 100 volts, 150 volts, and you can see that the copper is deposited at the cathode. We get electrolysis of the copper sulfate, copper at the cathode and oxygen at the anode. If I increase the voltage, you can hear the beaker vibrating, and we get electrolytic cold fusion. If I lower the voltage, (200 volts), 150 volts, 100 volts, we pass from cold fusion to electrolysis. Copper deposits at the cathode and oxygen at the anode. Now we're at 120 volts. I'm increasing to 200, 300, 350, and lowering to 200, 150, 100, and we get electrolysis of the copper sulfate. A positive anode, 350 volts, immerse the negative cathode, we get electrolytic cold fusion. Well, what happens if I put the cathode in first and then the anode? You can see that an insignificant reaction takes place. But what happens if I touch the glass with the anode? We get a reaction and the glass starts to crack. and melt. The glass continues to burn. Now I'll show you a sodium nitrate solution, and I'll break the glass jar which contains this solution, and you'll see that the glass catches fire by means of the liquid which leaks out through the cracks. Plasma forms which sets fire to the glass. Now I'll show you what happens to a solution of tin chloride. Anode on the left and cathode on the right. Increase the voltage and you get tin deposits at the cathode and electrolysis of the tin chloride. $100, 200, 250 volts, 300, 350, we get plasma without tin deposits. Now I'm lowering the voltage to 300 volts, 250, 200, 150, 100, and at 100 volts we get tin deposits on the cathode. You can carry out electrolytic cold fusion by starting from normal electrolysis of water. You immerse two electrodes in a salt solution, in this case sodium bicarbonate. We have the positive anode on the left and the negative cathode on the right. Now we apply an increasing voltage and we get electrolysis of the water. Oxygen at the anode to the left and hydrogen at the cathode on the right. If we increase the voltage now to 100 volts, 150, we get plasma. Let's increase the voltage to 170, 180. We can see that the plasma increases. 200, and plasma continues to form. We're at 200 volts, 250, 300, 300 volts, 350. Now I'll lower to 200, 150, 100 volts. It still forms at 80, 70, 60. At 50 volts we get electrolysis of the water. In graphite, I'll apply a voltage of 50 volts and we can see that oxygen forms at the anode and hydrogen at the cathode. If I increase to 80 volts, 100 volts, the reaction starts at 100 volts, 150 volts, 200 volts, 300 volts, 350 volts. The electrode has stopped working. This is another graphite cathode at 350 volts. Now let's have a closer look at this reaction. When we increase the voltage, we get hydrogen at the cathode. When we go over 150 volts, we get these sparks. As I lower the voltage to 100 volts, 120 volts, we're at 100 volts, 80 volts, here we get strong emission of infrared rays, which cause the camera images to appear blurred. We're at 150 volts. I'm increasing to 200, 250, 300, 350 volts. Now I'll show you some abnormal phenomena. I'll put two electrodes into this zinc sulfate solution, the positive anode on the left and the negative cathode on the right. I'll apply a voltage of 100 volts, and you can see that we get zinc deposits on the cathode. We get electrolysis of the zinc sulfate, oxygen at the anode and zinc at the cathode. If I increase the voltage to 200, 300 volts, we no longer get zinc deposits. But we get a violent cold fusion reaction. However, if I lower the voltage, we get zinc deposits. As I carry out the electrolytic cold fusion, I notice that a medium wave radio close by, which is turned on, has a lot of electromagnetic disturbance. So I ask myself, if I can see which radio emissions are emitted using a spectrum analyzer, I can establish which element reacted in this plasma which formed around the cathode. I was able to borrow a good spectrum analyzer which goes from almost 0 MHz to 26.9 GHz. With this spectrum analyzer, I was able to ascertain that there were specific emissions with certain specific frequencies. There was a powerful emission at 117 MHz, and I was able to establish that this was caused by the OH molecule. I realized that there is an excess of the OH molecule in solution, as if I touch this liquid after having carried out the electrolytic cold fusion for several hours, I see that my wet hands produce soap. This soap indicates the presence of excess OH ions in the solution. These ions cannot be produced by the electrolysis of the water, as water electrolysis always occurs when we have an oxygen atom emitted at the anode and two hydrogen atoms emitted at the cathode. So every time an oxygen atom transfers 2 electrons to the anode, 2 hydrogen atoms get 2 electrons from the cathode. So the OH ions cannot be in excess in normal water electrolysis. Then there's a second emission at 327 MHz. According to scientific tables, this emission can be shown to be a deuterium atom. At this point we need to establish how the deuterium atom was formed in the electrolytic solution. The water in the solution contains minute levels of deuterium, 1 deuterium atom for every 6,400 hydrogen atoms. So this strong deuterium emission at 327 MHz can only be interpreted as the on-the-spot creation of deuterium. How is deuterium created? Deuterium is composed of a nucleus which has a proton and a neutron. We already have the proton, the H+ hydrogen ion, which goes towards the cathode during electrolysis. Now we need to understand how the neutron in its nucleus is generated. The neutron can be generated by electronically capturing a proton. As a proton gets close to the cathode, it can absorb an electrode under certain conditions and change into a neutron and then bond to a nearby proton. This is clearly a reaction which absorbs energy, but this energy can be supplied by the electrical current generator we're using. At this stage, the formation of deuterium can be explained. We can explain the excess H+ ions as the proton, which was transformed into a neutron, created an imbalance in the oxygen-hydrogen ratio, whereby we get an excess of H+ ions, which I feel with my fingers. I can feel the soap if I rub my fingers together. The soap is produced by the H+ ions, in the same way as caustic soda. In the process of electrolytic cold fusion, we usually use tungsten electrodes, as this is the metal with the highest melting point, 3460 degrees Celsius. However, the process works with electrodes of any metal. Obviously, a metal with a low melting point will melt immediately. Electrolytic cold fusion also works with graphite or carbon electrodes, as long as they conduct electricity. I noticed something strange if you use aluminium electrodes. The aluminium melts, it almost seems to burn, to undergo combustion, and the residue that I find at the bottom of the beaker has a glassy appearance. Glass is composed of silicon oxide. The oxygen could come from the air during combustion, but I can't explain the presence of the silicon, as the aluminium used was 99.5% pure. As you can see from the periodic table of the elements, aluminium has an atomic weight of almost 27, while silicon comes straight after with an atomic weight of 28. This means that aluminium with an extra proton can be transformed into silicon. You can see from this photo of the screen of the spectrum analyzer I used in the experiment that on the left there are 0 MHz and on the right we have 2000 MHz. We can see these peaks. The two main peaks, the first on the left at 117 MHz and the second at 327 MHz. The first on the left is due to the OH molecule, and the second on the right is due to the deuterium atom. In addition, as you can see on the right, at 1420 MHz, there is no radio emission typical of the hydrogen atom. This means that the H+ atom is not involved in the formation of the plasma. There is also no sign of emissions typical of the water molecule at 21 GHz.